Hi and welcome to the solution of 8 challenge from Flare on 2019 competition. The challenge was called Snake, and let's start as usually from the message that we get. Okay, the Flare team is attempting to pivot to full-time Twitch streaming video games instead of reverse engineering computer software all day. We wrote our own classic NES game to stream content that nobody else has seen and watch those subscribers flow in. It turned out to be too hard for us to beat, so we gave up. See if you can beat it and capture the internet points that we failed to collect. So this is already gave us some information. It probably will be a NES game and we have to beat it. So probably reach certain score or play through all the levels. And from the title of this challenge, we can assume that it will be a Snake game. So let's start by actually playing the game, and I will be using this FCEUX emulator. I'll just open and select ROM file that we were given. Okay, let's just play, and we can see, so this is just a Snake game. We can collect some apples. I think those apples are, and the snakes grows. And I guess the challenge is to collect them probably too many that we can. So I guess we'll have to find some other way to finish the game and find the flag. Okay, but it's actually good to play the game a little bit to get some kind of understanding what the game is about, because it might help us during the reverse engineering of the file. But I guess it's enough. Okay, so let's just close it for now. Let's just return to our main desktop. So let's just open this file in Ghidra. And before we do that, we actually have to know a little bit about this NES format, and we can read it on the wiki page. There's like NES dev wiki, and actually this file format is described here. So the file contains a header, which is 16 bytes. Then there is this trainer, if present. And then there's a ROM data and character data. And this is important to know because our file also contains this header. So if we open in Ghidra, Ghidra will try to analyze starting from the header, but it doesn't make sense because there's like header information. This is not code. So when we open the file, it should actually ask if it wants to analyze, but I was already did that, so there's no question. But even though the analysis was being done, we could actually scroll down and start the analysis from this 16 byte, so 10 hexadecimal, and only here we see some actual data that it's meaningful. Okay. But if we scroll a little bit, we can see there are some addresses that are not valid. So those are written in red. And actually those are not that important, but later we'll see some of the values that are actually here. For example, like 27, it points to some code. But actually, if we would understand how this program or data and code is being loaded into the processor, and actually where it's in the memory, it's when it's being executed, we'll have to do some adjustment because those are not pointing to any code. It should point to something else. And we can also do that by reading again the same wiki page. There's some kind of CPU memory map that describes that, okay, we have some internal RAM, there are some addresses, and only from 4K it's the place where the cartridge is put. So we will have to move it to some addresses to actually get the correct addresses. But let's again maybe move to our emulator and see, because usually emulator has this option to actually show it the debugger. And debugger, when we just run it, it shows that we are executing at C23A. So, okay, that's something that gives us some info. But let's scroll up a little bit. And we can see that the first instruction that we saw in our disassembly is also here. So it's like C000. So this is the address that we should move our code in Ghidra to actually have a correct representation of this program in the disassembler. But also we have to remember that we have this 16-byte header. So actually we need to set our base address at BFFO. So that would be our starting address. Okay, that's one information. The other one is here, that actually the data, the code part in this NES file is only this 16K bytes. So actually it's like 4K hexadecimal, and our file is a bit bigger. So first what we need to do in Ghidra, we need to go to memory map, and we need to split this 6000 bytes file into two. So the first part would be this 4K bytes. So it should be 3FFF. So it gives us, no, actually it should be 4010 OF, exactly, because we have 16 characters of header and then 4000 hexadecimal characters of code. So we did the split, and then now we need to move this to another address. So this is the BFF0, and it gives end address as exactly where it should be, so like at the end of the range. So now when we did that, we have our code moved. Now we need to scroll, or just go to C000, and this is our starting address. So this is the place where the code starts, and now we see some red addresses, more of red addresses than we had before. And we could actually add some more memory maps segments here that would actually be mapping those addresses, but we don't need to do for all of those values because not all of them will be interest to us. So what we can do now, we can get back to our game again, and at least this debugger has something interesting also apart from the debugger part, which is this hex editor that actually shows the RAM values at offset 0. And if we play the game, we can see and identify places in memory that actually are storing useful information for us. So if we, like, for example, I just collected one apple, and you might notice that this value changed to 1. So let's just observe this value again when we collect the second apple. And collect 2 more, but this value changed to 3. So we know that at this offset 26 hexadecimal, it is stored the value that is storing the how many apples or how many points do we have in the game. Similarly, some other values in the first row, we can see if we move horizontally, one value is changed. If we move vertically, the other value change. So this is like here, this is the X position, this would be the Y position. I just need to change to the game. And if I pause, so this is the position of the, I guess, head of the snake, the Y position, this is the X position. So we identified 2 more variables that are very interesting to us. It might be, of course, the points. The points were somewhere here, 26 I think that was, and 8 I think, and 9th offsets were the X position and Y position of the head of the snake. So let's just go back to our Ghidra, and also maybe let's go back to our wiki. And if we look at this sample RAM map, it actually identifies some regions in this RAM. Like from 0 to F, we have 16 bytes of local variables and function arguments. And from 10 to FF, it gives us like global variables accessed most often. So we can actually add those regions to Ghidra. So let's just move it a little bit down, and let's just add some additional so locals. Let's call them locals, and we'll give 10. Sorry, that's the start address, so we'll start at 0 and we'll give 16 characters. And the second one is globals, and it starts at 10, and it's like FO. I think that's the correct length. Okay, and having that, we can also rename those values, because they will be somewhere here at address 0. Local, it's locals. So we let's maybe go back again to our game. Let's just, so it's 0, 1, 2, 3, 4, 5, 6, 7. 7 is snake position position Y. So this is the, so 0, 1, 2, 3, 4, 5, 6, 7 is the snake's head position. So we can find here the 7. So this is snake X pos, and the next one would be snake Y position. And then again the points. Let's just try to find where was the points. That's really difficult game. So the points are here. So it's like 20, 21, 22, 23, 24, 25. Is that correct? 0, 1, 2, 3, 4, 5. Okay. 25th would be the 25th would be the points. And we have here points. Okay, so that's something. We can save it now, and then we can start analyzing our code. So we already see that, okay, there's one place that actually writes this address. We can go here and yeah, it actually tells us, okay, points are being stored here. And we can see that actually there's like a 0 is loaded to A, and A is stored at points. 0 is loaded to A, and then it's stored at 26. So we can actually assume this is some kind of initialization code that actually resets the points after, like for example, after we fail, or like, yeah, or we start the game. So that's one thing that already tell us something. But okay, but that was only the one place that actually was this points being referenced. That's not very good, because we could assume that this should be more. Like for example, if we grab an apple, we should get at least points should be changed. We should get another point, but it wasn't visible. But we can also see that some parts of the code were not disassembled. So we can just press here and press the D key, and some more code revealed with already identified places like points here also. Okay, so we can maybe go back to our code and see if the points were getting more references than before. Okay, we have already 2. So this is the place, and we can also scroll down and we can see there are some undefined that actually doesn't give us code, but if we skip those, we can identify more places with the code that might be interesting to us. Okay, and also like, I guess 0 and here gives us some more code. So actually Ghidra didn't identify all the places with useful code. I don't know if it's like a problem or those were not referenced directly, so it just skipped those. But anyway, you can always identify hex values that you think are code and then just disassemble them in Ghidra. It's like the default binding. Okay, let's just go to our points again. Let's see if we did get any more places where reference the points. Okay, not yet, so we need to scroll a little bit more to see if we can identify more places with useful code. Okay, there's For now, we just don't analyze it. We just try to identify as many code as possible. Okay, we can see some more code being identified. Okay, we could actually try to see if there are points, but let's just go even further. Okay, there's some more code. If it doesn't work, we can just skip some of the characters. It might be that there are some bytes injected into the file to prevent such analysis, because it's if you try to put some bogus numbers, it might mean that Ghidra or any other disassembler will not recognize it as a valid opcode, and it will stop the compiler. So we can see also some points being referenced here and some snake position. So actually, yeah, it's actually interesting. And also, I already know, but there's also some interesting that we add one, we store in points, and then also we compare with like 3 hexadecimal, so quite a big number. So this might be something of interest to us. So maybe let's see what will happen if we put a breakpoint on this address in our emulator. So this one has an option to put a breakpoint. So let's just C833, I think that was the address. Let's just confirm it. C833, correct. And we want a breakpoint on execute. Okay, and let's unpause our game. Okay, so we actually hit the breakpoint. So right now A has 3. So it's actually that we have 3 apples eaten. So it actually compares how many apples we eaten with 33. That's interesting. So maybe let's just try to set that we actually have 33 apples and just run the game again. And we can already see that game speeds up. So now it's faster, the snakes move faster. Okay, so something, it looks like we get to the next level. So it actually means that we would have to collect 33 hexadecimal apples to get to the next level. But okay, we didn't get the flag yet. But let's try to collect another apple, which is kind of difficult because of the speed, but maybe we'll manage. Okay, so again, we land up in the same address and it checks again. Okay, we collect 1 apple with the higher speed. So let's just change it to 33 again. So the comparison will succeed. And again, the snake is moving even faster than before. And we could actually try to get this apple, but we didn't have to, because at some point the apple will be randomly put in the correct row. So yeah, so again, in this place, we compare the 1 apple that we just collected with the 33. So again, let's just change to 33 and run again. Okay, even faster. I'm not sure if I will be able to play this game with this speed, but maybe we can wait and maybe we'll get at some point an apple in the correct row. And this is what happened. So again, the same place, the same comparison, we'll just change it again. And we got the flag. So it was like, I don't know, 4 levels we need to beat with increasing speed. So we had to collect 33 hexadecimal apples to get the flag. And yeah, when we did that, of course, with cheating, we got the flag, which is narpas sword@flareon.com. So that's how you could solve the 8th challenge, which was called Snake. I think it was quite interesting, quite interesting because it actually was well, using different assembly. I'm not that skilled with 6502 assembly code, but anyway, yeah, it was nice to learn and nice to use Ghidra to do the analysis and found the interesting code and yeah, test it in the debugger and yeah, finally get the flag. So I hope you like this solution. I hope you learned something. If so, please like and subscribe, and see you next time on solving the 9th challenge from Flare on 2019 competition. Bye!